Imagine with me, if you will, you have found yourself a small asteroid. Has a radius of 1 meter and a very particular mass. 1.499 times 10 to the times 10 to the 12 kilograms. This thing is a very dense, very small asteroid. Contrived, so it works out nicely for this problem. On the surface of this small asteroid, on the surface of the small, asteroid, we place a very small and very dense 1 kilogram mass. So this is a very, very particular, totally ridiculous scenario. We have a small asteroid, this big across, so a big circle, exercise ball, with a mass of 1.49925 times 10 to the 12 kilograms. An asteroid of that mass and of that size would be incredibly dense. Basically, what we're probably dealing with is a neutron star at this point, just for interest's sake. But let's say we have an asteroid. And next to that asteroid, we're going to place a very small, think like the size of a pea, so that its radius doesn't really impact what's going on here. 1 kilogram mass. So imagine a teeny tiny ball bearing or a pea, the weight of a kilogram. Okay? We're talking densities. Yeah, densities on the order of like approaching a neutron star. Okay? We want to find the weight, i.e. the gravitational force of that 1 kilogram mass, for reasons that are going to become obvious as soon as we plug these numbers in. So I got Fg equals big G, big M, little m over r squared. It's going to be 6.67 times 10 to the negative 11. 1.49925 times 10 to the 12. 1. And because this mass is so small, we're ignoring its radius. So we're going to assume that the radius, the distance between their centers, is basically just the radius of that asteroid, which we're going to call 1. I want to square that. If you run those numbers, what do you get? Totally contrived to give us a lovely number.
Pretty much 100.
What is it exactly?
99.999975.
Cool. So 100.
Yeah. I don't know. Well, also I had a
Okay. So the reason that we're doing that is this. If Fg is equal to 100 newtons, and the radius on the bottom is 1, and this mass here was 1, what this is going to allow us to do is to write this expression down here. That my force of gravity is equal to 100 over r squared. Because big G, big M, and little m remain constant. And those things multiplied together are 100. Ashton.
This is related to yesterday's lesson, but I kind of had an idea of a question.
Okay.
I was watching this episode of Family Guy, and
of course you were.
Okay, but Peter was like getting like too heavy or whatever, so Brian made a joke saying how Peter was so fat he had his own field of orbit, so that he dropped some fruits
and
around, and they started orbiting, and I was gonna see what will be required, or how heavy would Peter have to be for that to actually work.
Well, there's a few problems with that. First of all, just dropping a fruit in there isn't going to cause it to orbit. It would just fling into him. They'd have to give it the appropriate sideways velocity.
Assuming that, Brian.
Well, you pull up later. What I want you to do is I want you to pull up the episode. Okay. Find this. Do you know what piece of fruit it is?
It was like apples, bananas.
You're going to do this later.
Okay.
You're going to find, were they all orbiting at the same radius? Okay, so you're gonna have to. We're gonna estimate some things here. Estimate, distances. There's no reason why you couldn't figure that out. Okay, so unrelated to Ashton's random question, Fg equals 100 over r squared is what we're going to use here. Now imagine that we move this mass outwards away from the center of the small asteroid. We want to find the gravitational force at the following distances from the center. So we've got this. We've got Fg equals 100 over r squared. The reason that we like this excuse me, is because it makes inserting these different radiuses really, really nice. At this point right here, at 1 meter, the force is going to be 100 newtons. At the 2 meter mark, I just take 2, shove it into R. 2 squared is 4. 100 over 4 is 25 newtons. 3, not as nice, but still pretty nice. This is going to be 100 over 9. Anyone know what 100 over 9 is?
11.1 repeating.
It is 11.1 repeating. We're going to shove 4 in here. That's going to become 4 squared is 16. 100 over 16 is? It is 6.25. Sure, he's just punched him into his calculator. He's good, but he's not that good. 5. This one's a hard one. 5 squared is 25. 100 over 25 is? 4. No calculator needed for that one, I hope. 6. 6 squared is 36. 100 over 36, Ashton? 2.7 repeating. And we're just going to jump all the way out to 10. This one should be pretty obvious. 100 over 10 squared. 100 over 100, that's 1. Okay, so that is the force of gravity on this object from this object as I move it out. So the force is variable. So the force, it is variable with distance. So what do we do when we have forces that change as you move away from them? Oh, no. What do we do with them to analyze them? We graph them! Here we go. Flip the page. Okay, so here we go. At 1 meter, this distance is measured in meters. This force is measured in newtons. So we have a force distance graph. At 1 meter, 100 newtons. 2 meters, 25 newtons. So this thing's dropped off fairly aggressively. So here we are down at 25. At 3, we're at 11.1. So it's going to be like right there. At 4, we're at 6.25. At 5, we're at 4. At 6, we're at there-ish. And at 10, we're going to be down here. Because each one of these lines represents 10. And, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. We have 10 lines. Take us up to 100. Each one's worth 10. So our graph looks something like that. So if this was a lab and I was really particular, either we'd do this with a computer or you'd get something called a French curve. French curve is not as fun as it sounds. It's basically a ruler shaped like a teardrop. It would help us draw something looks like this. For the sake of this, freehand it, but freehand it nicely.
He's creating webs. So.
Where is he?
Right here.
Like what?
Like right here.
Like right in front of your face?
Yeah, right here.
Oh, a little guy.
Yeah.
Okay, well, either ignore him or kill him.
No, I don't want to do that.
Yeah, that's a very tiny spider.
Cool.
Okay, well, you keep doing your thing. I'm going to keep doing my thing. So, there are 2 ways that we typically analyze graphs like this. Find the slope or we find the area. Obviously, a slope's going to be problematic here. Things not linear. So we find the area.
Let's go. Yes. I know how to do this.
Okay, so recall the area under a force distance graph is equal to what? The work. So, if we were to find the area under the force distance graph, effectively what we would be doing is we would be finding the amount of work required to drag an object from the surface of your small asteroid out to 10 meters. That would be all of this area here. Okay? That's the area that we're looking for. At this stage, the majority of you are only qualified to solve this by counting blocks. Okay? Physics 12, and the best we can do is counting blocks. There is a small subset of you, though, that could solve this another way. What's the alternative way to solve this then? Don't you dare.
The fundamental theorem of calculus.
Fundamental theorem of calculus says what?
You find the antiderivative of.
Okay, so crash course in calculus for some of you. To find the area under a function like this, assuming we know the function, we do know the function fg is equal to 100 over r squared. To find the work required, we need the area under the graph. The area under the graph is the sum of the integral of fg with respect to, well, in this case, r. This little s is the worst thing that happened to mathematics for most of you, and most of you haven't been introduced to it yet. This is the sign for integration. Integration is just a summation of infinitely thin little rectangles. So they took the idea that it's a sum, and they made this cool little s, the integral symbol, symbolizing that we are going to sum up a whole bunch of infinitely thin rectangles between our x-axis and our function. You said derivative. Then you said integral. And we're going to take the integral of this from 1 to 10. Calculus students, what is that? The rest of you, if you want, can count squares. Joseph, I want you to count the squares. Go. Joseph and Garcelle, count the squares. Each square is worth 10. So count the squares. Yeah. The rest of you guys are doing integrals. So, okay, let's just integrate this. We have 100. Basically, I'm integrating, gentlemen, 1 to 10 of 1 over r squared. How do I integrate that? Just tell me what the, yeah, what's it? What's the integral of 1 over r squared? Or do we have to send this back to our calculus student at the back? Crystal. Oh, it's negative 1 over r?
Yeah, it would be negative 100 over r. Because you bring the r up, you...
This becomes the integral, so 100, integral from 1 to 10 of r to the negative 2. dr. So then this is going to become, so we're cool with this, negative 100 over r. Okay, evaluated from 1 to 10. So it's going to become negative 100 over 10 minus negative 100 over 1. Joseph and Garcelle, do you have a number of squares for us yet? No, this is why we like calculus. Well, learning calculus is harder than learning how to count blocks.
I can do this for my project.
No, we just did it. It's too late. But there are some very interesting physics applications you could look at doing for your project, yes. That is what, after you take the integral, basically, we've taken the integral. It gave us this new function, and we're evaluating it between 1 and 10. That's what this line means. So this is going to become minus 100. That's just going to become 100 minus 10. Gives us 90. Joseph, you got a number of squares for us yet? So the alternative way to do this is to do what Joseph's been taking forever to do. And count the number of squares. All the coffee fairies are here. Can we let them in? While we wait, let's count. That's 1. That's 2. That's 3. This is basically 4, and we'll just take a little smidgen of one from over here. We'll call this 5, and we got a little smidgen going on over here. 6, and we'll take that little chunk there. Let's go 7. And we'll take a little bit of this over here. 8 plus this guy. That's a half. These 3 are basically going to give us 9.
Because I did it in fractions, so it's like it's
So I don't know how he gets quite so specific. So basically, by counting it out, you can estimate. We've got 9-ish squares. Each square is 1 by 10. So each one of these squares is 10 Newton meters, which is 10 joules. So 9 squares is approximately equal to 90 joules of work, of energy required to do that work. Or you can just do the integral, and there we are. Next year, if you're taking physics, those of you who are going off to university, you will absolutely have to do this the integration way. But you'll learn all of that in semester 1. So we have found the work required by analyzing the force distance graph for an object, tiny object moved from a slightly larger object. Comments, questions, concerns about what just happened? That's an entire course. Just accept that you'll learn how to do it one day. If there's no questions about the calculus, are we cool with the procedure? Yeah. Well, and graphing what we've got here, recognizing that a force distance graph, the area under it's going to give us the work. We're cool with that? Not a lot of nodding going on. We'll just assume that it's early on a Tuesday morning. Flip the page. Okay. So, we have found that the work is equal to the change in this guy here, negative GM over R. On the previous page when I integrated it. So if I flip back, remember this 100 here, that's big G, big M times little m. That's where that 100 came from. So basically what I did at the bottom there was I took the integral of FG with respect to R, which was the integral of GMM over R squared with respect to R, and I got that this thing is equal to negative GMM over R evaluated between somewhere and somewhere else. I'm up? Okay. What are the units of that thing? Oh, joules because it's work. Okay, we like that. Give me some other units for it.
Newton meter.
Well,
You don't know? Calculus. Me and Blake do. We're so good. You can run calculus right now.
That's a little weird. I think math 12 is even if it's 12.
Okay, so what are the units of that thing? You guys have said joules because it's work. Okay, what are Newton meters? Well, okay, so this units are joules. The units are, what were the units of, well, yeah, work is a force times a distance, Newton meters. This particular function is the change, or the change in this function is the work done. Work equals to change in what? We had a definition for work. If work is the change in this, based on the calculus that we've done, work is equal to change in, oh, we don't have it here. The definition of work is change in energy. Work is equal to change in energy. We have two kinds of energy that we've dealt with so far. We've had kinetic energy, which that expression is not going to change. And we've had potential energy. M little g times h. Ashton has already just outed it. This function here, negative g, big M, little m, over r, must be equal to your potential energy in universal gravitation. So it used to be mgh is now negative gmm over r. And this, ladies and gentlemen, was on your formula sheet. Right here. So I'm going to remake this formula sheet because I'm sick of these things being in different spots and I keep forgetting it. But it is important for you guys to recognize that this, gravitation, and this are both connected to universal gravitation. We have the force due to gravity, and now we've got the potential energy in a universal gravitational field. I will explain that in a second. Ritzai, I think, is on the next page. Yes, Ritzai is on the next page. Flip it over. Here we go. So we're going to use this new formulation for the potential energy to find the exact value for the work done. We're going to get the same value we've got now twice. We're going to do it again. Except we're going to use the work energy theorem. Work energy theorem said this. Energy initial plus the work done is going to be equal to energy final. What kind of energy does our object have here at the beginning? Potential, and only potential because the sucker's not moving. So we'll say this is PEI plus work is not moving at the end. Begins and ends at rest, we're told. So it has potential energy at the end. So we're going to use the expression that we've got, negative GMM over R plus work, our initial. It's going to be equal to negative GMM over our final. So work is going to equal negative GMM over our final minus negative GMM over our initial. So we found that the work, we've done this already, this GMM piece here, that's 100. It's based on the mass of the asteroids. So it's going to be negative 100 over 10 plus 100 over 1 equals 90 joules. A third time, we've come up with the exact same thing. And here's what's really interesting. While it took us 90 joules of work to move this thing 10 meters away, how much work is it going to take us to move this object infinitely far away? I want to take this object here and I want to move it to the other end of the universe as far away from this asteroid as we can possibly get. Sorry, Blake? Oh, Zach? It's not 90 joules. It's barely more, is the really interesting part. So let's look at it again. We've got, just using the same expression. I've got negative 100 over our final plus 100 over 1. This is my initial. This is my final. If I take my radius and I extend it out to infinity, if I take the limit as my radius extends to infinity, 100. This is going to be the work equals negative 100 over infinity plus 100 over 1. As this number gets really, really big in the denominator here, this is going to basically approach what? 0. My calculus students are cool with that. Do the rest of us accept that that's true? Okay? Like if I make this like 100 million. 100 over 100 million is 1 over a million. It's 0.000001. Okay? So this is basically going to go to 0, which means that the work done to take this object and throw it away to infinity as far across the universe as we possibly can get it is only going to be 100 joules. 10 more joules than it took us to get it up to 10 meters.
So are you saying that even if you're like infinitely far away from that object you technically still have a tiny, infinitely small sliver of gravitational force on you from that object?
Yes.
So
it's effectively 0, but it's never actually 0. But because it's effectively 0, in math, they care about the difference between effectively and is. In physics, we don't. Because effectively 0 is 0 for all intents and purposes. Do you feel the gravitational pull from the sun on you right now? As far as you're aware, no. I mean, you don't necessarily feel the gravitational effect of the Earth on you now either because you've always been there. So that was a really bad question. But you don't necessarily, you're not aware. We understand that the Earth, the gravity that doesn't exist is pulling you towards the center of the planet. You're not like ever so often getting pulled upwards as the sun orbits its way around the sun. Sometimes you feel a little bit lighter because the Earth is a little bit closer to the sun on a portion of its orbit. That never happens. Though the sun is impacting you gravitationally, you just don't experience it. The other really interesting one, probably the more useful one, would be the moon. Because the moon has obvious gravitational effects on our planet. The tides. You don't feel that pull, though the tides do. So they're constantly shifting, but you don't necessarily feel the fact that sometimes the moon is closer, sometimes the moon's a little further away, and the tides are shifting as a result. So effectively, even though it's not like mathematically 0, is basically 0. And that's good enough.
But technically we're experiencing gravitational.
From every other object in the known universe, you're experiencing gravitational pull.
It's like a random person.
Anything that has mass is affecting you gravitationally. Any object that has mass is impacting you gravitationally, is what the math would say. Practically, we can ignore it all because almost all of them are 0. Flip the page. Oh, sorry. We just did this on the previous slide when I made R go out to infinity, so flip the page again. So, here is a hand-wavy kind of argument. We said earlier that this MGH piece here was potential energy. That was true. It worked. When? At or near the surface of Earth. Because this little g was 9.8, and we were just able to use it times the height times the mass of our object. This little g is just... Let's analyze this here a little bit. This little g here is what? What's another expression for it? Don't tell me it's 9.8. What's the expression for it? G, big M over R squared, where R is... Yeah, well, the distance from your object to the center of the Earth. Now we're multiplying it by little m here. And we're multiplying it by h. H is just what? It's the height above the planet, right? So this is going to be, if we actually get really, really picky here, at or near the surface of Earth, because the radius of the surface of Earth, the radius of Earth is what? 6,380,000 meters. Adding 10, 20, 100 meters isn't really going to change that number a whole lot, right? That's it. Okay. Mathematically, it will change it a little bit. But as far as the physics goes, is there really any difference between 6,380,000 and 6,380,100? Practically, is there like that big of a difference? See, now this is the difference between physics and math. Math would say, yeah, 100 is the difference. Physics says, yeah, it's basically nothing. So on orders of magnitude is how physicists like to talk. Orders of magnitude, when we're talking about 6 million, 100's not a lot. Even 1,000 isn't a lot when we're talking about 6 million of something. So this h is basically just what? Nope, it's not. Don't you say it's 0. It's not 0. Nope, h is not 1. This h represented before your height above the planet. Using universal gravitation, we're not measuring your height above the planet anymore, we're measuring your height from the center of the planet. So this is basically just r. Which means that gravitational potential energy is just m times gm over r. Which we've already proven. So that potential energy equation that we had, mgh, works very well. Okay, if we get really technical, this isn't just r, it's r, well, it's, this h is, it's actually some height minus r. But that height is so small that, you know. So the expression that we used before, mgh, and negative gmm over r, basically equivalent. Yep.
You could use mgm over r instead of mgh.
At or near the surface of Earth, you don't want to deal with the hassle. Yeah, there's some stuff that's gonna rise here. You could. You aren't gonna want to.
What about on the surface of another planet?
At or near the surface of any object, mgh is the more useful expression. When you're dealing with substantial distances from substantial objects, this is the one that you want to deal with. Okay? Because you've got this mg kind of FG force. When you are at or near the surface of any object, mgh is what you want to work with. When you are away from the surface of a massive object, it's this negative gmm over r that you want to deal with here. But I'm hoping I've convinced you that they are functionally equivalent. Just one is more useful in certain circumstances, and the other is more useful in certain circumstances. This one, mgh, assumes that little g isn't variable. And for all intents and purposes, it's not. So you can use this. Technically it is, because you could go to even just on the surface of Earth, you could go to different places on the surface of Earth and measure different values for little g. They're very small differences, but they're there, they're measurable. As soon as you look at how r is changing, now you got to start dealing with calculus. We don't want to deal with calculus for obvious reasons. So mgh. Cool? So, 0 for our original potential energy was determined by the height above the surface, yeah? Or whatever we called 0. Usually we called it above whatever surface we were dealing with. So like my desk here, if I want the potential energy for my pen, let's say, I would measure the difference between the height, well, the height it is above this desk, because there is no, well, there's a very small chance, but looking at the nature of the pen lid, if I just drop this thing, it's not going to roll onto the floor. So if I wanted the potential energy of my pen, I would just consider my desk surface to be 0. Yes? I drop it. Oh, look, now it has no more potential energy because it fell. The problem with universal gravitational potential energy is that where the heck do we put 0? With little mgh, it's easy. And it can change depending on the context of the problem. Where is 0 with this? Negative gmm over r. Well, unlike mgh, where 0 is at ground level, this new potential energy is only 0 when? Don't flip back. I will flip back. You stay there. When is potential energy equal to 0? That's a really interesting thought, but it's not at the center of the object. because I'm going to flip back further at the center, because this is just technically this is asymptotic. Like this is just going to keep going up and up and up and up and up and up and up forever. Things get really weird when we go inside objects with mass. Gravity gets weird. So let's go back and look at the math. Where is potential energy 0? When R equals infinity. So in this particular thing, with universal gravitation, let's go back a step. With original potential energy, MGH, we said 0 was at the surface and we moved things away. With this, universal gravitation, we move things towards 0, because 0 is infinitely far away. So we say PE equals negative GMM over R. As R goes to infinity, PE goes to 0. And it's negative the whole time, which is interesting. So it's negative coming up to 0. It's weird. Graphically, we can look at it like this. I've got negative potential energy. I'm adding work to it, which is going to give me a potential energy equal to 0. That's again weird. We're putting work into something to get it infinitely far away from an object. So all of these arguments give us this expression, which I've written down before. We're going to write it down again with some of this justification. Potential energy equals negative G, big M, little m, over R relative to 0 at infinity. And if you look at the little acrostic I just made, that's where your RTZI is coming from. So that exists just at the front there to remind us that that is gravitational potential energy with relative to 0 at infinity. So it's set that way. Joseph, you were in my psychology class. You know I write things down very intentionally. You just didn't. Okay, cool. Comments, questions, concerns? One more example here, and then you guys are going to play with this stuff. What's happening here? A missile is launched from Earth. Its fuel is used in an initial burst. So this is quite like when we say missile, we mean missile in the traditional sense of missile. Like all of the energy gets expanded at once, and then there's no more like adding energy to the system. This isn't missile launched from your jet fighter that has a rocket engine and it's just going to go now forever. This is boom, big explosion happens. This thing gets launched and away it's going. Okay, that's the kind of problem that we're dealing with here. If we don't do it that way, things get very, very difficult. What happens to things as this object rises? Here's the surface.
Is there any work being done to select?
All the work is being inserted into it at the beginning. So there's no work being added past this red line. Boom! Massive influx of work at the red line. Rocket just goes. That's going to give it a massive initial what? Massive initial kinetic energy, well, specifically VI. What's going to happen as the rocket flies further and further and further away? Okay. Kinetic energy decreases.
Is it still in the atmosphere?
Well, it has to be. It'll start decreasing immediately,
Oh, okay.
and nothing is going to happen to it to help it increase. That make sense?
I was just thinking space, but I guess it still has a little bit of.
We're not yet, but we don't start on space. We start on the surface. So we're not in deep space. There's still the gravity of the planet. We're ignoring the air resistance on the rocket. That would be massive air resistance on the rocket. We're ignoring that because we don't have the capability of dealing with that. K is decreasing. What's happening to the force of gravity, though, is this thing gets further and further away. Okay, as you get further away, Fg decreases. But as you get further away, what happens to potential energy? It increases. Yeah, I see what you did there, Zach. So Ke is decreasing, Pe is increasing. We expect that makes sense. Fg also decreases as you get further and further away. It decreases pretty quickly. Out here, when R is equal to, so we can answer this relatively easily right now. Which of these is the best option? Potential energy is increasing, kinetic energy is decreasing. That's C. Using the reasoning that we just gave. Let's look at what happens when R is at, when this thing's infinitely far away. As the rocket gets infinitely far away, what's going to happen? PE is going to be 0. KE is going to be constant. It could be 0. It might not be 0. Could be 0.
Oh, it's like it,
Depends how much energy you gave it right here. Yeah, it could, theoretically. Yeah. Yeah, Korea, they're right. All the work technically was done here at the beginning. Basically, this is what I wanted you guys to recognize, that PE would be at infinity, PE is 0 and KE is a constant. KE could be 0. We don't know. But the potential energy is 0. At that point, KE is no longer changing. It's a little different, yeah? Comments, questions, concerns about any of the stuff that we've done today? Questions that you're not sure how to articulate? Things that you're just uncomfortable about? Perfect. Love that. That's where I want to keep you. I want you to play with this stuff. There's not a lot. There's less questions today than there have been. I just got to make sure I'm consistent. This is lesson what? Lesson 6. Yeah, here's what I'm assigning you. I want you the following questions. 1 to 4 and 9. That's all I'm giving to you. I do like question 7. That's okay. I have a room. I can fit it in there. Guys, I do want you to flip back for a sec. I'm going to make a declaration here. We are going to call at infinity. We're going to say that K has reached 0. Potential energy has been used. The increase in potential, it has come at the cost of a decrease in kinetic, which is what happens, and at the maximum potential energy, when potential energy finally reaches 0 from some negative value, coming up to reach 0, KE is 0. So all the kinetic energy, no, it wasn't taken out of the system, it was converted. All of the potential energy that existed at the beginning, or the kinetic energy that existed at the beginning, increased potential energy to 0. Okay? So the only way the work energy theorem actually works is if kinetic energy is 0 at infinity. Okay, so that's what we're going to do. Otherwise, number 9 is not doable.
It's not. You know, because it's not. It's just fun. On the surface of Earth. So, like,
I am going to toss one more in there, guys. I also want you number 7. 7's a getter. It's just one question. It's not the end of the world. There you go. There you go.